In today's video we're going to be talking about the transpose of a matrix, so let's get right into that. If we go to matrix A, and I haven't specified A size, let's see why in a minute, and it's got element A11, A12 all the way up to A1n, so where n's the number of columns, and then it's got however many rows. It's got a m a m1, so m is the number of rows, and these go down, whatever. And there's not just one more here. There could be, these dots mean there could be however many down. In this bottom right corner we've got a m n. Right, so that's the A11 done. So these numbers in the subscript represent the position of each element, and when we take A transpose and we represent transpose with a little t, what we're doing is we just, for each of these elements, A, I, J, we're just moving it to A, J, I. So A11, well, that just becomes A11 because you're swapping the 1 and 1 around. But A12 becomes A21. So this element moves here. Okay. AM1 becomes A1M, so M actually becomes, instead of the number of rows, M becomes the number of columns, so this element goes all the way up to the end here, and it might not necessarily be in the same position as that one, but it becomes the first element, the last element in the first row, or in the first element in the last column as well. Yeah, so all we're doing is, and this might seem a little bit complicated, but all we're doing is swapping the rows and columns around. So let's do an example. It's easier with square matrices, but you can do it with others. 7, 3, 1, 4, 2, 2, 0, 1, 5. Now the transpose of that, well, 7, 3, 1, the first row just becomes the first column. 4, 2, 2, the second row just becomes the second column, and the third row just becomes the third column. Okay, all the diagonal elements stay in the same place, but that's pretty simple. So let's just call this M, and then this is M transpose. Okay, now we'll look at some properties. If we transpose A and then we transpose that, it just gives us A. Pretty simple one. I mean, just look at this example. We swap the rows and columns. If we swap the rows and columns again, we just get back to where we were in the beginning. Nice and easy. Now, if we multiply A by some scalar, lambda, and we take the transpose of that, that's just equal to lambda of transpose of A, and that makes sense because when you swap these rows and columns, I mean, you're not doing anything to lambda, so lambda just remains unchanged. Now if you do A plus B and you transpose that, plus or minus, that's equal to A transpose plus or minus B transpose. I'd recommend you to check that out for yourself. Just call a matrix A. A and B have to be the same size, obviously, but as we've shown in a previous video for addition and subtraction. But apart from that, so pick two matrices of the same size, add them up, take the transpose, and then take the transpose of each and add them up. Maybe do that for a specific example, and then think about how you can show that that works generally. Maybe we'll go through that example in tomorrow's video. And the final property is if you take A, B, and you multiply them together, take the transpose, that's equal to B transpose multiplied by A transpose. That's another one I suggest you go through, and we will go through that at some point as well, so you can see the solution if you do try to do it. But for now, I hope you enjoyed this video on the transpose of a matrix. I hope it cleared up what it is and some of its properties. If you did enjoy, please like and subscribe, and I hope to see you in the next